For this week, I've chosen the topic of the Milky Way. So officially, this would be once around the Milky Way, which might take a little bit longer than usual for some of the talks. But anyway, here's a magnificent picture of the Milky Way going across the sky from the horizon to horizon down to the right where the sunset is there, taken not by myself, but by somebody else from NASA down there. From the southern hemisphere. You always get the best views from the southern hemisphere, as we will see. But the original sort of story of the Milky Way goes back a very long time. Ancient people with no light pollution to contend with were able to see it very clearly arching across the sky to different or lesser extent, depending on which part of the world they were from. And they saw it as a milky, faint patch of light or stripe of light going across the sky, and noticed a few things about that. They noticed immediately that it always stayed in the same place relative to the stars around it, so it seemed to move with the fixed stars as the sky wheeled overhead. And as you see on the screen here, Aristotle had a good think about what it might be, and I'll quote here, the translation here. He said that the Milky Way might be the ignition of fiery exhalations of some stars which were large, numerous, and close together. That's quite an interesting description, and he sort of got the idea that it might be a lot of stars packed very close together, but he didn't assume that it was that as such. He thought it was some sort of fiery gas or exhalation that had come from a lot of closely packed stars. He then said the ignition takes place in the upper part of the atmosphere in the region of the world which is continuous with the heavenly motions. In other words, it was in the realm of the fixed stars, which was deemed to be the outer reaches of the known world in the sky, beyond the realm of the planets and everything else that moved. So he sort of got it right that it was moving like that, but of course it's not in the upper part of the atmosphere at all. But he thought it was some sort of burning gas very high in the sky, I suppose. So he sort of partly noticed a few things that were right, partly got it wrong. The first record we can find of the idea definitely being that it is a myriad of stars packed tightly together is from Persian, Middle Eastern philosophers and astronomers. And this particular gentleman whose seal we have at the upper right of the screen in Arabic and whose name I can never pronounce, particularly said that this was a myriad of tiny stars packed together in the sphere of the fixed stars, and that the stars are larger than planets. And I'm not quite sure how he worked that out, other than perhaps that he thought that the realm of the fixed stars was much further away. But therefore these things must be larger if we can see them at all. So he's almost on the right track. Of course, he didn't have the benefit of the telescope, and it was Galileo, of course, who got the first opportunity to take the newly invented telescope, pointed at the stars, and figured out in his book here that the Milky Way was thousands and thousands of stars packed together, and the telescope resolved the smudgy, milky look of it into individual stars, bringing the resolution that nobody else had been able to achieve. But the first person that figured out that the Milky Way was probably what we would now call the plane of our galaxy was this philosopher, Immanuel Kant. Very much did it on the basis of other people's studies and results and thinking about what might cause them. And he proposed the Milky Way might be this great structure of stars whirling together, held together by gravity. He was speaking after Kepler's laws and Newton's law of gravity and so on had all been explained to describe how planets orbit in the solar system. So he figured that the galaxy might have a self-gravitating structure as a whirling disk of many stars all orbiting around a common center of mass, and very much got that right. Now, the tricky bit, of course, is when you look at our galaxy from inside, we see very much this band of light, the individual stars within it, and the dark, dusty lanes carving across that structure. But it's very difficult to figure out what shape it is. We have to really infer it by looking at all the other galaxies. In particular, we've got the Outer Limits galaxy at the bottom here, NGC 891, which shows that dark dust lane carving across the center and a orangey looking bulge in the middle and the bluer looking outstretched spiral arms. When we look at that, if you imagine that stretched and wrapped around the sky, then it matches up the image that we see of being inside our own galaxy. This central bulge of the galaxy in the Milky Way corresponds to this region with the dark dust lanes across it. So it sort of makes sense, but we have to do it by looking at other galaxies and then trying to figure out which structures match what we can see of our own. 1785, William Herschel had the first serious go at mapping the galaxy, and with the Gaia satellite up there now doing it in exquisite accuracy and mapping the 3D positions of 1 billion stars, better time to celebrate the work of Herschel here, because this diagram that he drew looks a little bit like some sort of tentacled sea monster. Is actually quite a scientific approach to solving the problem. He's plotted us in the center here, this dark spot in the middle of the diagram, and every other dot there is a bright star that he observed and catalogued its position, and he's plotted them radially out from the center of the position where we are, according to their sky coordinates, mapping the 3D of the sky down onto 2 dimensions to get it onto a sheet of paper. And for the radial dimension, the distance from the center, he has used the brightness of the star as seen from the Earth. And what he said about this was that he knew it was a gross approximation, but he said that he had no way of knowing if all stars were equally powerful, but if he assumed that they were all roughly the same, and their differences in brightness were solely therefore due to the standard candle effect of distance, where the brightness of an object, if you double the distance, you'll see it a quarter as bright. He said, well, I don't know the true power, but if I just use distance as a proxy, or use brightness as a proxy for distance, I can plot them out on the diagram, and that's what he's done here. And what you can see is it's resulted in a shape that is longer along the horizontal axis than it is vertically, so a flattened structure, and that it's got these 2 very long arms out this side with a gap between them where there was nothing observed, and that it's unsymmetrical, and that there are more stars to one side than the other. And as we will see, that's actually not a bad representation of the geometry of our galaxy. Now, the story goes on that we were observing these other galaxies out in space, although back in the day they were referred to as nebulae, meaning cloud of gas, because we couldn't resolve them well enough to truly see the structure. Lord Rosse, with his enormous 72-inch reflector, was the first to really see the spiral structure in these so-called nebulae. And in particular, the Whirlpool Nebula, drawing on the left there, is one of his, where it could well have been some sort of spiral, whirling, hurricane-like structure of gas and dust whirling around in a cloud inside our galaxy. But some people were beginning to think that actually Immanuel Kant's idea of the Milky Way galaxy might well mean that these objects were other galaxies further away outside the Milky Way. And this argument raged for many years, culminating in the great debate in the 1920s in America between Harlow Shapley and Herbert Curtis. Shapley was arguing that the Milky Way was the entire universe and that the spiral nebulae were just clouds of whirling gas and dust inside the Milky Way, and that the whole universe was therefore roughly 50,000 light years across, because that seemed to be the size estimate that was best for the size of the Milky Way. Whereas Herbert Curtis, leading a group of others, argued that the spiral nebulae were what he termed separate island universes, separate as in outside of the Milky Way. And if the Milky Way was a universe, these were other separate island universes. We now call these things galaxies, and the term island universe has really been consigned to the bin of history. One thing that he showed was that there were more novae, more flare stars and exploding stars in the Andromeda Nebula than there was observed in the whole of the rest of the Milky Way. And he argued that if these were just exploding stars, then it showed that the Andromeda Nebula probably had more stars than there were in the whole of the Milky Way. And if that was the case, then it was a larger, separate galaxy, not part of our own, because it would have been far too small to have had that many stars in it. He also studied these objects, globular clusters. We see these orbiting around the outside of the Milky Way. We have about 400 or 500 of them that have been detected, and they consist of hundreds of thousands to about 1 million stars for the largest, all tightly packed together in these roughly spherical structures and often containing very, very old stars. And Shapley produced a map of the distribution of galaxies around the Milky Way. And what this showed was that if we plotted them on galactic coordinates as little red dots like this, and here we have the sun, then there were far more of them to one side than there are to the other. And this very much suggested that if they were symmetrically distributed around some center, then we were off to the side of that center, and therefore perhaps identified that we were off center relative to the galaxy if the center of the distribution of clusters was all centered on the center of mass of our galaxy. That's what this all made sense and supported the general estimate of the size of the galaxy. It also identified our place within it and matches that map from Herschel rather well with the unsymmetrical shape and distribution. So we now have a picture somewhat like this of our galaxy with a central bulge and a flat disk, rather like two fried eggs back to back, surrounded by this swarm of these globular clusters. And the interesting thing was that we were able to measure the distance to some of those globular clusters, and that goes back to what we talked about in an earlier lecture about sizing the universe and the use of Cepheid variables to pin down the distances. The Cepheid variables, just as a recap, are a special type of variable star named after the lead star of the class, Delta Cepheid, that pulsate in brightness on a regular basis, and the rate of pulsation is directly proportional to their overall power output. So we can infer that they're standard candles and use them from their apparent brightness to infer distance. So they were used to help map the globular clusters. And we were also able to then have this man, Edwin Hubble, solve the debate once and for all by identifying a Cepheid variable in the Andromeda Nebula. Marked on the diagram up here in this little box, he's written N and crossed it out, N for nova, because he realized it was repeating its cycles and therefore was a Cepheid variable. And he showed, using that distance to period relationship, that the Andromeda Nebula was at least 1 million light years away, which was 20 times the distance to any known object in and around the Milky Way, including all those globular clusters. And therefore, the Andromeda Nebula was in fact the Andromeda Galaxy and a separate island universe, to use that term, thus ending that great debate. So nowadays, when we look at the Milky Way, we have lots of other tools available to us. This is the picture of the center of the Milky Way, taken from the southern hemisphere. We've got the central bulge here, showing that orangey color, orange because it contains no new stars, and therefore only old stars. And the only stars that get to live to be old are the slow burning yellow, orange and red dwarf stars. All the more exciting hot white and blue stars live fast and die young, and therefore burn out and blow up. And so where you see hot young blue stars, you know that there's been recent star formation, and there just hasn't been any in the center. Whereas in the spiral arms, as we will see, there's lots of it. You also see the dust lane across the middle very nicely, leading out towards the spiral arms. But we can use different wavelengths these days. Another of Herschel's discoveries, in fact, was infrared radiation. But we've now got telescopes that can take us from the visible into the infrared, the microwaves, the ultraviolet, the X-ray, gamma ray, radio waves, right the way across all the possible size ranges and energy levels of these electromagnetic waves. So here's an all sky picture taken of the Milky Way in infrared. This shape, this elliptical shape, is where we've unwrapped the whole sky from a sphere onto a two-dimensional surface and kept the shape correct. So it's a projection. And again, you can see the bulge of the Milky Way in the middle, and we're beginning to see through some of that dust, because infrared can often penetrate through the dust better than normal visible light can. We can go to longer wavelengths, and the galaxy looks like this, which is interesting in itself. We're now seeing the cold gas rather than the hot and warm objects, and we're including fingers of cold gas that go out in great loops around the galaxy like this. And these are evidence that points to how the galaxy formed by merging lots of smaller galaxies together. We could also go the other way to high energies, to X-rays, and look at very hot gas, and we find that it's confined to the plane of the Milky Way, and with a number of very hot spots, one right in the center here, and others out in other regions. Here is the Crab Nebula that we talked about last week, glowing in X-rays. There are another couple of pulsars, the Baylor pulsar and the Geminiga pulsars, very bright sources of X-rays in our galaxy. But we've also got this thing here. This is a distant galaxy, Blazar 3c, the Cambridge Third Survey, 454.3, goes by the exciting catalogue number. And this is way off and across the far side of the universe. It's a quasar that's emitting very strongly in the X-rays that you don't see in the other pictures. So of course, there's the Crab Nebula taken in high resolution, showing the spinning pulsar and the jets emerging from it. So that's what these pulsars inside the Milky Way look like. So using all those tools, we've been able to put together a map of the galaxy as if we were looking down on it from the galactic North Pole. And what we find is the spiral arms whirling around the center. And we are here, the sun and the solar system, in the what's Douglas Adams described as the less fashionable quarter of the Orion spur, which is itself a separate little spiral armlet that forks away from the main Sagittarius arm back here. It splits in two. There's one piece that goes around this way and one in which we are that almost crosses back outwards. So what we see from the sun looking in towards the center, which is seen from the southern hemisphere of the Earth, because our south pole points in that general direction, is the bright nucleus and the thick star clouds of the constellations of Sagittarius, which are made up of material in the Sagittarius and Centaurus spiral arms in the main. And when we look the other way out, we see the constellation of Orion, and through beyond Orion, in the Orion spur, we then see the next layer of stars in the Perseus arm. It's very noticeable if you look in the distances of the catalogue distances of things like star clusters and nebulae, that from the northern hemisphere we tend to see a first rank of objects that are about 1200 to 1600 light years away, and those are all in the Orion spur. And then there's an enormous void between there and about 7,000 light years, which is the next band of material, and that's in the Perseus arm, and we see another whole cluster of those. And then there's another void until you get to the thinner regions of the outer arm, much fainter. So we can see it already just in the structure of the pattern of distances to objects, and the same works going the other way, only it tends to be more dense towards the middle. Now, you also have seen in that previous picture that we think that the Milky Way has a bar across the center, and there are competing theories about that. Some people don't believe that there's a bar at all. Others believe it's a short bar, 3,500 light years long. Others that it's a long bar. And some people even argue that we have two. So I'll leave that there for you, borrowing from a joke that Mickey gave at the Cambridge Young Astronomers. Thank you, Mickey. We just don't know quite what's happening in the middle there because we can't see very well. But we do have some idea of some of the interesting things that are going on deep within the galactic center. So let's have a look. Well, surrounding that bar of gas, we think there is a ring of material that's much denser. So it's about 15,000 light years from the center. We're at about 27,000 light years. So it's sort of halfway between the center and us. There's this ring with a lot of hydrogen gas and a lot of new star forming regions. And of course, these go with tending to attract a lot of dust and material. That's why we can't see very well. But if we were viewing it from outside our galaxy, this would probably be a very prominent feature in the Milky Way. But if we dive right into the center, this is a real picture that's been synthesized by taking all the different optical, infrared, ultraviolet and X-ray pictures, merging them together. This is the sort of structure that's going on right in the center. What we've got deep in the middle here is an X-ray source called Sagittarius A star, which we think is right at the hub of everything, right in the central region. And then lots of others. And there's another one that I'm going to talk about, which is this dark dust cloud over here to the left that you can see stretching away quite a long distance. And that's a giant molecular cloud of dirty, dusty material called Sagittarius B2. So we're going to have a look at what these two objects are and the interaction between them. So Sagittarius A star, X-rays right from the center of the galaxy, and we think these X-rays are coming from a disk of matter that is swirling around and being sucked into a supermassive black hole. So it's deep in the middle of the galaxy in here, and we can drill into that with a high resolution X-ray image and see various hot gas regions, but in particular the brightest source is indicated there as Sagittarius A star. But our instruments are so good we can zoom in further on that region. We find a star cluster, and right in the center of the star cluster we find the hot ring of gas, very bright in the center, in the little inset there. That's the most detailed resolution picture we've got. What we're looking at is the hot gas surrounding the central object that is emitting in X-rays, probably has a temperature around 1,000,000 degrees, and is moving in a spiral in towards the center under the gravity of the object in the middle. What we can't see is the black hole itself. Now you may recall there was a fantastic image of the accretion disk and the black hole in the center of the large elliptical galaxy M87, published a couple of years ago now, using what was termed the Event Horizon Telescope. That's a telescope comprising lots of radio telescopes from the whole of the Earth, all combined to give the highest resolution photograph ever. Now they have been attempting to synthesize a picture of the black hole, which would be right in the center of this little disk here, for some time now, but they've not yet published the image that they're creating. So there's been various technical difficulties, one of which is that it's changing and moving over time, and so the usual trick of taking a long exposure is resulting in a blurred image. So having problems with trying to do the detailed photography, but fairly soon we should get an even more high resolution image of what's going on right in the center. What we have done is studied the stars in that star cluster right in the center and plotted their movement in orbit around this unseen object, which is marked at position with the red cross there. And you can see these stars are orbiting in the classic elliptical paths. Of course, it's in 3D and flattened here, so some of these look very long and thin due to the effect of perspective, and we have to figure all of that out, which you can do using spectroscopy to work out the motion. But we've got one particular star, which is this one. That's called S2, which is in a very handy elliptical orbit that's pretty much face on to us and goes around in 15 years. And so it's very straightforward when you have an orbiting object like this to use Kepler's laws and Newton's formula for gravity and work out the mass in the center. And I get my various young astronomy students who are doing GCSE to do this, and they come out with a figure at around about 4 million solar masses, all concentrated where the red X is. And you can do the same calculation for other members of the star group, you get the same answer. But I want to draw your attention to the one on the very thin orbit that comes in from top left. Look how close that goes to the X. It goes even closer than the star S2 does. It's going so close, in fact, that the size of the object that's in the center, that's controlling all the others under gravity, is smaller than the orbit of Saturn around the sun. That's still quite a big object, but the only way to pack 4 million solar masses into such a small space is for it to be a black hole. And of course, we can't see the object, so that all points to very solid evidence of a supermassive black hole there. And of course, we think all galaxies have such a supermassive black hole in them. So that's the object Sagittarius A star. It's a 4 million solar mass black hole with an accretion disk around it. pouring out X-rays from the accretion disk as the matter is spiraling inwards. Now, I was going to say a few words about the molecular cloud Sagittarius B2. It's hit the news for a couple of reasons. It's a giant molecular cloud, so a thing like the Orion Nebula in some senses, 390 light years from the center of Sagittarius A star and 150 light years across. There's 3 million solar masses of material in this cloud itself. So if it all collapsed, it would make another black hole about the same mass as the supermassive one. In fact, there is a star cluster growing within it. It's forming lots of new stars. So it's not collapsing into a single object. Temperature cold, as is often the case for these clouds of gas. If they were hot, the molecules would soon escape. So they have to be cold to retain their existence, but just 40 degrees above absolute zero. And we've been studying it intensely, looking to see what it's made of. There's obviously lots of hydrogen gas there. There's quite a lot of silicon dust grains, various metal silicates, carbon in the dust, that sort of thing. But we've also been able to use radio telescopes to do spectroscopy and pick up lots of interesting molecules. And the first two are ethanol, ordinary alcohol, as you would drink in an alcoholic beverage, and another one called ethyl formate, given the chemical formulae there, but I won't bore you with the details. There's a whole list of other things in there that would make a cocktail of this rather a knockout. It's got ether in it, so that wouldn't do you any good if you drank it. Propylene oxide, very volatile and nasty. Methyl formate, methanol, lots of meths in there, and propylene cyanide as well. But the interesting one that hit the news was the ethyl formate, this molecule here, because this would mean that if you took that, it would smell of raspberries and taste of rum. So ethyl formate is what gives rum and partly what gives raspberries their characteristic flavour. And so you could make a raspberry daiquiri out of material from Sagittarius B2. And there is more ethanol there than all of the oceans of the Earth contain water by a factor of 1 billion to 1. So they're not messing about. There's they say there's a bar at the center of the Milky Way. Well, it seems that it's been serving raspberry daiquiris. The other interesting thing that caused B2 to hit the news was that it was giving off X-rays. And you don't normally get X-rays from a cold region of gas. Well, it turns out that this was a temporary phenomenon, and you can see in the 4 images to the right, taken at different times by different X-ray telescopes. So we've got 94, 2000, 2004, 2005, and the color indicates the temperature with red colors and white meaning hottest. So the Chandra in 2000 saw this patch of B2 flare up in hot X-rays and then cool off again. And you can see the first photograph was catching it on the rise in temperature. So this hot spot developed and then faded away. Very curious feature indeed. It turned out it was effectively energy from Sagittarius A star, from the accretion disk of the black hole, being thrown out as high energy X and gamma rays across the 350 light year gap from Sagittarius A star to Sagittarius B, and that was then lighting up the gas in Sagittarius B2, energizing it to emit X-rays, which have then come back to us. And so what happened was that 350 years ago, relative time, actually, of course, both of these objects are 26,000 light years from us. So 26,350 years ago, Sagittarius A star flared up and sent an enormous pulse of energy out all over the galaxy. Some of it came straight to us, but some of it went sideways, hit Sagittarius B2 350 years later, and we're now seeing the echo of that illumination coming the 26,000 light years direct back to us. So some of the light took a longer path by going sideways for 350 years and then being bounced back in our direction. But we can compute the brightness and figure out that Sagittarius A star must have been outputting 1,000,000 times as much energy during the outburst that caused this reflection as it is today. So it was probably feeding voraciously on something that fell into it and output 1,000,000 times the power output for a period of about 12 years while it consumed this meal and then faded back to normal. And the direct pulse of X and gamma ray light, 1,000,000 times stronger than the current emissions, would have arrived on Earth about 300 years ago. And interestingly enough, if you look back at the climate record, that's in the period around about the time of Newton and the time of the Little Ice Age. And in fact, there was a sudden cooling of the Earth's climate recorded, which we don't really have a proper explanation for, in around about 1650 AD, which could well have been the influence of this direct pulse of X and gamma rays from Sagittarius A star, taking 26,000 years to get straight to us. And then we're seeing the light echo of it 350 years later, having bounced off Sagittarius B2 and taken two sides of a long thin triangle. Now there was a near miss not so long ago with a cloud of gas and dust that's shown here in the yellow, orange, red and white and blue positions, swinging past the red cross that marks the position of the supermassive black hole. It was on one of these elliptical orbit paths, and we thought it was going to fall in and be shredded, but it actually moved through past and escaped. But it was distorted and stretched and probably lost some material to the accretion disk on the way past, but it didn't create a fantastic increase in the brightness of Sagittarius A star. But it's interesting to think that had it done so, it might again have sent vast amounts of gamma rays our way, and these would affect the upper atmosphere, perhaps destroying the ozone layer, doing other photochemical damage in the process. So the life on Earth it's still dependent on this. And if we look back even further in time to 6 million years ago, certainly the black hole was very, very active then, because it has left the trace of these two enormous Fermi bubbles of hot energized gas above and below the plane of the Milky Way. The Fermi bubbles emit in X-rays and gamma rays and are the result of the jets of material that will shot out along the polar spin axis of the black hole. Black holes are terribly messy eaters. Material spirals in down the accretion disk, gets very hot and ionized, and then gets tangled up with the magnetic field of the black hole, which is spun and twisted into great helices that come out as jets along the spin axis, and that carries these enormous jets outwards, and it's spun and whirled around because it's not perfectly aligned to the plane of the galaxy, so it's filled out these two enormous bubbles of hot gas. And as I said, this was a relic of a vast eruption 6 million years ago, and so our very, very early ancestors, who were still probably swinging around in the trees at this point, might well have observed the center of our black hole, center of our galaxy, being an immensely bright object back at that time. Now the Sun, of course, orbits around the center of the galaxy and obeys the laws of gravity in the process. So it takes an orbit around the common center of mass, and we estimate that orbit takes between 225 and 250 million years to complete. So a galactic year is around about 230 million years, say. We're not certain, and it does vary a little bit because the Sun's path is dependent on the distribution of matter in and around the spiral arms, and so that can speed us up or slow us down a little bit. The speed that we're traveling at, 500,000 miles an hour, is a terrific rate. It's a tenth of the speed of light. So, 0.1% of the speed of light, a tenth of a percent. And that's enough to start worrying about in terms of calculating things with needing to worry about relativity if you want to get the right answer. Since the formation of the Milky Way galaxy, there have been around about 13 billion years. Since the Sun was born about 5 billion years ago, it has therefore gone round 21 times. So it's 21 galactic years, which is a reasonable number to conjure with. And you can look at the chronology of Earth's history in terms of galactic years. Makes quite an interesting way of doing it, and without the numbers becoming very large. But the path of the Sun is quite strange in some ways, in that it's also got an up and down wobble induced, and that wobble is induced by the interactions with the density waves of the spiral arms. So it's not going round just in one flat plane, and again that's partly what makes the orbit slightly difficult to predict. Sorry if this diagram's a little bit busy, but we've got the galactic plane marked in the blue here, with Sagittarius A star in the middle here, and the galactic North Pole, South Pole in blue. And the Sun at 26,000 light years away, orbiting around the center, as I've said. And the solar system is oriented at an angle like this, such that the plane of Earth's orbit gives us the North Pole of the solar system, which is pointing out in this direction. And then the Earth is orbiting around that with another tilt of 23 degrees and giving us the North Pole of the Earth. And so they're not perfectly aligned, but the North Pole of the galaxy, the North Pole of our sky are broadly aligned, and the South Pole and the southern skies are pointing towards the southern part of the galaxy. And this tends to mean we can actually see the center of the galaxy better from the southern hemisphere than we can from the northern hemisphere. I'm afraid this diagram takes a little bit of getting your head around in terms of the 3D aspects of it. But those periodic wobbles carrying us above and below the plane of the solar system are quite interesting, because every 30 million years or so, we cross through the plane of the galaxy. At the moment, we're around 7,000 light years above the plane of the galaxy and moving towards the extreme position. But we will turn around and go back down again. So we passed through the center a number of million years ago, and we'll dip back down again and go back through it again. And in fact, it was about 11 or 12 million years ago that we last passed through the central plane. Now, this diagram here shows the rate at which craters have been forming on the Earth over the last 300 million years. So now here, going backwards in time, the rate at which new craters have been formed has not been a constant and has wobbled up and down. And if it looks like it's getting less in time, that's an artifact that craters get rubbed out over time. And so, in fact, there were more craters being formed in the past than there are now. It's just that we can't find them all because they get erased. But nevertheless, over any short time window of this, the relative change is not affected by that. The crucial point is you can see it's peaky. And we've marked some of the particular large crater events, such as the Chicxulub crater that took out the dinosaurs at 66 million years ago, was part of a particularly heavy period of bombardment. But there have been others, and some of the other large craters are also at or near the peaks of other larger bombardments. What's more interesting is that the interval between these particular bombardments is not exactly constant, but it's of the order of every 30 million years or so. And the last time, as I say, we passed through the plane of the galaxy was here, when there was another large bombardment, or medium-sized bombardment, with no particularly large crater formed that we know of. So maybe these cratering events are controlled by our movement through the plane of the galaxy. Here's another view of the same thing. And here we've plotted extinction events in orange and craters in red. And you can see that there is a rough pattern in the intervals between cratering, between extinction events, 25 to 30 million years or so, and the same interval, roughly speaking, between major cratering events. So one set of geologists argue that the extinctions are caused by cratering events, and that's certainly the favoured explanation for the Chicxulub dinosaur extinction. But it seems that a lot of these extinction events may have an extraterrestrial origin. The other side of things, people argue that no, it's actually volcanic eruptions causing flood basalt events, pouring enormous amounts of sulfur dioxide and carbon dioxide into the atmosphere and wrecking the environment, and it's nothing to do with cratering. And so if we plot flood basalt events on the same chart, they line up quite well with many of the major extinction events, in particular the Chicxulub one. So scientists are on both sides of this. Is it an impact? Was it the Denon traps in India erupting? You know, there are some flood basalt events that don't seem to lead to extinctions. So I tend to be, with my astronomical bias, in favour perhaps of impacts. But the connection has recently been made with the idea that maybe both the incidence of impacts and the flood basalt eruptions are both linked to the same astronomical cause, and that cause being our crossing of the galactic plane. And the hypothesis is that as we cross through the galactic plane, where there is a concentration of dark matter, this mysterious substance that we've never detected, that accounts for 3/4 of the mass of our galaxy or more, and is subject almost entirely to the law of gravity alone, and probably interacts via the weak force, which is also responsible for the radioactivity of heavy elements, but not to electromagnetism or anything else. So we can't see it with ordinary light or any other of our telescope instruments. But if that dark matter is spread in a thin disk and is particularly dense in the plane of the Milky Way, as the Earth passes through it, large amounts of dark matter would sweep through the central core of the Earth. And if they did so and either got trapped there or were present there in large enough numbers, then perhaps they could interact via the weak nuclear force with the dense heavy elements that are trapped in the central core of the Earth and lead to a burst of additional radioactive decay or other nuclear processes involving the decay of dark matter that we don't yet understand, but nevertheless cause a burst of energy to be released in the core of the planet. And that might produce an enormous magma plume, which would lead to a flood basalt volcanic eruption that could well be the root cause of this. So the impacts increase because of all of the interaction of the Oort cloud with the dirt and dust of the galactic plane, throwing millions of comets into the inner solar system, increasing the cratering rate on the Earth and risking extinctions. And at the same time, dark matter is upsetting the energy balance of the Earth's core and causing it to release enormous amounts of volcanic eruptions. So maybe this is why both occur simultaneously, and we will never be able to separate the one from the other because they're both caused by this 30 million year galactic plane crossing. In which case, it's been 11 or 12 million years since we last did it. So the good news is that we have quite a long time, 18 million years or so, before the next round of doom from the galaxy and our orbit around it. So you don't need to worry about it coming to get us next Wednesday. And with that, I shall bring it to a close. Thank you very much.